Okay, this is part 2 looking at the binomial distribution for us. And so in this one we're looking at on-time flights. So according to flightstats.com, American Airlines flights from Dallas to Chicago are on time 80% of the time. So suppose that 15 flights are randomly selected, the number of on-time flights are recorded. So from here we can see that n is 15, and then our probability for success is 0.80 or 80%. Okay, they are definitely independent because they're randomly selected, and mutually exclusive because we have success or failure, either on time or you're not. And so that would be part A. Why is it binomial? We have a fixed number, n equals 15. We have a probability of success, and we've got mutually exclusive outcomes, success or failure, on time or not. So part B says find and interpret the probability that exactly 10 flights are on time. So this is going to be the probability that 10 of our flights are on time. And so we want to know when I should say the probability that x equals 10. Okay, so I'm going to go over to StatCrunch and get under the stat calculator binomial. Okay, we have got 15 trials, probability of success is 0.8, and we want to know exactly, so that's going to be equal to 10. So in 15 trials there is a 10.32 or point. Let's go back over to this screen. So it'll be a 0.1032% probability that exactly 10 flights. That's not 10 or more or 10 or less, that's exactly 10 in a trial of 15. Okay. Part C. Oh, so and then interpret. So the way you'd interpret that is you'd say something like, okay, if there's a 10% chance, 10.32% chance, if we were to do a study of, so I guess I'll just kind of write this out. But if we were, say, if we were to go to the 100th place, in 100 trials of this study, we expect about 10 of those trials to have exactly 10 on-time flights. Okay, and you can bump it up into 1,000 trials. That would be 100 and about 103. So you go to the 1,000th place. So that's just the interpretation of it. Okay, so part C. What if we are fewer than 10? So you got to think of your numbers fewer than 10. So I've got 15 trials, 0.8 is my probability. Fewer than 10, those numbers are going to be 9, 8, 7, 6. So that's going to be less than 10, but not equal to, because we are fewer than 10. So 0.0611. So again, we need to interpret this as probability that x is less than, strictly less than 10, which is 0.0611, which is pretty low. So if we were in 100 trials, we would expect about, because the 100th place is 6. In 100 trials of this study, we would expect about 6 to have fewer than 10 flights that are on time. Okay, D, probability of that at least 10. So again, at least, you got to interpret that. So if you're at least 10, then that's going to be 10, 11, 12. So this is going to be the probability that x is greater than or equal to 10. So I'm going to come over here. I'm going to change this to greater than or equal to 10. And we get 93.89%, 0.983. .9389. Wow, I am just not on my game today. 0.9389. And so for this, we would say, again, in 100 trials of this study, we expect about 94, because that would round up to 0.94, 94 to have at least 10 flights that are on time. Okay, now part E, find the probability that we're between 8 and 10 flights inclusive that are on time. So this is the probability that X is between 10 and 8, so it's greater than or equal to 8, but less than or equal to 10, so it's somewhere between 8 and 10. Inclusive means it can include 8 and 10, so this is going to be the probability of 8, 9, or 10. And over here on this calculator, notice right up above there's a between button. So I can change it from standard to a between. My N and my P are still the same, but now I notice they are less than or equal to signs, so this is 8 and 10. So we get about 0.16 on that. So we'd expect about 16 out of 100 to have exactly, or to have somewhere between 8 and 10 flights that are on time. Okay, so looking at sneeze. So according to a study done by Nick Wilson of Otago University, Wellington, the probability of randomly selecting an individual will cover his or her mouth with a tissue, handkerchief, or elbows, and that's the method recommended by public health officials when sneezing, is 0.047. So let's suppose you sit on a bench in a mall and observe some people's habits as they sneeze. And first we want to know, what is the probability that among 15, so we've got 15 randomly observed sneezing individuals, exactly 2 cover their mouth with the tissue or a handkerchief. So the probability of success here, so this is P, is going to equal 0.047. And so in part A, N is going to be 15. We can assume independence, so success is they cover, failure is they don't. So what's the probability that we get exactly 2? So we're going to jump back over, and I'm going to be in the standard. So N is 15, probability of success is 0.047. Whoops, not 2 decimal place. There we go. And we want it to be exactly, so equal to 2. So that'd be 12.4, so 0.1240. 1240. Okay. Then part B. So what's the probability that among 15 randomly observed sneezing individuals, fewer than 3 cover their mouth? So again, you have to think of, what does fewer than 3 mean? So this is the probability that X is going to be less than 3. So it'll be 2, 1, or 0. Okay. So I'm going to come back over into StatCrunch. And same N, same P, but now we're less than 3. Okay. So that's going to be 0.9691. Okay. So that's the probability that fewer than 3 will cover their nose. And then part C, would you be surprised if after observing 15 individuals, or sneezing individuals, more than 3 cover the mouth with the tissue, handkerchief, or elbow? So this is going to be, the probability that we are more than 4. And will we be surprised? So let's check out what's the probability. So this would be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, or 15. So it's much easier to just do what we call a cumulative here using StatCrunch. So that probability is teeny. So that probability is 0.0005. So would we be surprised? Yes, actually very surprised, because that probability is so small. Okay. So now we're going to talk about the mean, or the expected value, and standard deviation of a binomial random variable. So in a binomial experiment with n independent trials, probability of success is p. Here's how we find the mean and standard deviation. The mean is just n times p. Okay, the number of independent trials times the probability of success. The standard deviation is n times p times 1 minus p, so the number of trials times the probability of success times the probability of failure, and then you got to take the square root of that again because we're standard deviation. It's kind of nice. So also for a fixed p, as the number of trials n in a binomial experiment increases, the probability distribution of x becomes bell-shaped. As a rule of thumb, if n times p times 1 minus p is greater than or equal to 10, the probability distribution will be approximately bell-shaped. We are going to use that quite a bit in the future, but just as a note there, as the number of trials gets big, we'll start to see a bell-shaped curve. Okay, so in this question, looking at, so I don't know what's with the sneezing and now the toilet flushing, kind of taking everything to the bathroom here, but these are just the questions that I not randomly picked, but I felt that went over the concepts well. So in a healthy hand washing survey conducted by Bradley Corporations, it was found that 64% of adult Americans operate the flusher of the toilet in public restrooms with their foot. So that's going to be our probability of success is 0.64. So if 500 adult Americans are randomly selected, how many would we expect to flush toilets in a public restroom with their foot? So that would be what's our mean. Okay, and we know that n was 500. So the mean is going to be 500 times 0.64. Okay, and that'd be 280. So we get 280 on that. Would it be unusual to observe 280 adults who flush a toilet in a public restroom with their foot? Oh, sorry, I just totally botched that calculation. I was looking down at the wrong part. So this is 320. So would it be unusual to observe 280 who flush toilets in public restrooms with their foot? This is part A. Part B. So again, we still have n is equal to 500. And we want to know, in this case, what's the probability that x is equal to 280? That's kind of the thing we're looking at. But we need a standard deviation to see kind of where, how many standard deviations, because this is very large sample sizes. So if we're a lot of standard deviations away from the mean, then it would be unusual. If we're close, then it would not necessarily be unusual. So the standard deviation is n, square root of n times p times 1 minus p. And that is equal to 10.73. So 320, if our standard deviation is 10.73, 320 is our mean, and 280 is almost 4 standard deviations below the mean. So 280 is more than 3 standard deviations below the mean, which is very unusual. And so in this case, it would be unusual to observe 280 because it's so far below the mean. So it's a terrible 3 there, but that is a 3. So if you recall back to when we looked at our empirical rule, the 68, 95, 99.7, 99.7% of the data lies between 3 standard deviations above and below the mean, which means 0.3% of the data is either above or below 3 standard deviations. And this is almost 4 below. And so this would be very unusual to observe. So that's a look at the binomial distribution. There's how you do it in StatCrunch.